Hello students, today we'll be learning about Taylor series method. In the previous lectures we are discussing single step method. We have already completed Picard's method in the series. Now we have Taylor series method. Again, it is a single step method and it is the most fundamental method, and it is the standard to which we compare the accuracy of the various other numerical methods to solve the first order differential equation. So consider the IVP dy by dx is equal to f of xy with the initial conditions y at x naught is equal to y naught. Now let y is equal to fx be the exact solution. So the Taylor series expansion of yx at the point x is equal to x naught is given by the equation 1. Now in this equation, if we substitute x minus x naught as h, then the resultant equation would be this: y at x1 is equal to y naught plus h times y naught dash plus h square by 2 factorial y naught double dash plus h cube by 3 factorial y naught triple dash, and so on. So this is the approximate solution of y at the point x1. On the similar basis, if we want to calculate the approximate solution of y at the point x2, then we could have it as y at x1 plus h, which is equal to y1 plus h times y1 dash plus h square by 2 factorial y1 double dash, and so on. So we can generalize this and we can have a general expression for the Taylor series method of order n. So this is the formula for order n. Now let us move ahead to the questions so that we can easily understand how to answer such kind of questions. Now I have already written the question here. Y at 0.1, to find y at 0.1 to the initial value problem, dy by dx is equal to minus 2xy square. Given y0 is equal to 1, that is, this is the initial condition that we have, with h as 0.1. H is the step length which is given to us. Using the Taylor series method of order 4. Order 4 means that you have to find out the Taylor series expansion up till order 4. Here x0 is 0, y0 is 1, h is 0.1. Now what is x1? x1 is x0 plus h. We know it. So x0 is 0, h is 0.1. So x1, the next point, x0 is 0, so x1 would be 0.1. And we have to calculate the value of y at 0.1. So our Taylor series expansion for yx is given by the equation 1. Y at x1 is equal to y0 plus h times y0 dash plus h square by 2 factorial y0 triple dash h cube by 3 factorial y0 triple dash, plus there would be h4 by 4 factorial y0 fourth derivative, and so on, because we have to calculate up till order 4. Now, how would we calculate these values? We know the value of y0, but how would we find out y0 dash, y0 double dash, and so on? For this, we will use our IVP. Our IVP is given as y dash is equal to minus 2xy square. So here we know x0 is 0 and y0 is 1. So y dash is equal to minus 2 times of x0 into y0 square. So we will be able to get the value of y0 dash, that is 0. Now what is the double derivative of this? Just differentiate y dash x so that you can calculate the double derivative, which is minus 2y square minus 4 times x by y dash. Now again, at the initial point, that is x0, y0, when we will calculate the double derivative, we will get the answer as minus 2. Now we come to the third derivative. The third derivative, we will differentiate the double derivative and we get the answer as this. So at the initial point x0, y0, we are getting y triple dash as 0. For the fourth derivative, we'll differentiate the triple derivative and we'll get the solution as this. Again, at the initial point x0, y0, I am getting the answer as 24. Now, using all these values and substituting it in the first equation that we have written above, the Taylor series expansion, I'll get 1, that is y naught, plus 0.1 into y naught dash, plus 0.1 whole square by 2 factorial into y naught double dash, and so on. Calculating these values after addition and subtraction, I am getting y at 0.1 is equal to 0.9901. So this is how we could calculate the value of y at 0.1. Now let us consider another question which is different from the above question. Try to understand the question first. Use Taylor series method to solve dy by dx is equal to x minus y with the initial conditions y at 0 is equal to 1. Now what we have to do, this is our IVP. Use Taylor series method to solve the equation at x. So at x and then at x is equal to 0.1 and 0.2. So in this question, what we have to find out first? We are not given h here, but yes, we can obviously calculate our h. It is easily visible that h is 0.1. But if it is not mentioned in the question, how could we find out the value at the Taylor series at x? We have done the Taylor series at x is equal to x naught in the text portion. So we'll be using that only. Y of x is equal to y naught plus x times y naught dash plus x square by 2 factorial y naught double dash, and so on. Now calculating all the values in this on the similar basis, we'll get y dash is x minus y. So at the initial point x naught y naught dash is minus 1. Now the double derivative is 1 minus y dash. So at the initial point I am getting the value as 2. Now triple derivative of y is minus y double dash. So at the initial point I am getting minus 2. The fourth derivative, it is not necessary to calculate the fourth derivative every time, but in this I have done it. It is your choice. If you don't want to do it, you can do with the three derivatives only. So moving in the same procedure, we can now substitute the values in the equation 1 and I'll get my answer as y at x is equal to 1 minus x plus x square minus x cube by 3 plus x4 by 12. This is my Taylor series expansion at x. Now, the next I had to find out the value at 0.1 and 0.2. Now it is very easy. In this equation 2, just substitute 0.1, x as 0.1 and x as 0.2, and you were able to calculate the value of y at that particular point. So you will notice here in this question, I have just substituted in place of x 0.1 and I am able to get the y at 0.1 as 0.9097 approximately. Similarly, when we put x is equal to 0.2 in the equation 2, we will get the value of y at 0.2, that is equal to 0.837466, or we could say that approximately y at 0.2 is 0.83747. So in the upcoming lecture, we'll be doing one more question of Taylor series method. So thank you so much.